Okay, I think we should get started. I'm Jun Nakajima from Intel. I've been working on virtualization Xen for a long time, more than a decade. I actually attended the first Xen Summit. I think that happened in Cambridge. It was 2005, something like that. Anyway, so I've been working on Xen for probably for longest time, I guess. Anyway, so today I'll just provide a quick overview of new hardware features and also what we are doing, especially how we are enabling those hardware features in Xen. Okay. I had one feature plan, but unfortunately that didn't go public today, so that's kind of sad, but anyway, I have many things here, so hopefully you can see what we are doing, okay? So this is the usual stuff. You know, many people are saying data is the new oil of the digital economy, right? And it's no doubt that you know that we are seeing very large data growth, and that continue to happen. And then as we have more data, we have more demand. For example, the IoT or AI machine learning. IoT devices are generating a lot of data, right? And the data is sent to the compute, backend, the cloud, and then the cloud needs to compute and process. We also know that AI or machine learning systems become more efficient as they have more data, right? So my point here is basically the data growth will push more demand across all the computing and the resource and security and the real time, and then monitoring, performance monitoring, and other areas. So I'll look at each of them, except probably network. And then, just to provide a quick overview of what kind of hardware features we have. Okay. So one is the data, and then we are very serious about the data growth. And then one feature we are adding is this 5-level page table, as you guys know. The background of this one is we need to have more physical addressing, okay? And probably you guys know if we have a 64-bit virtual address support, doesn't mean all the 64-bit address space is available, right? We just have a limited 40-something address space for the virtual address space. So what's happening is we are extending the virtual address to support more physical addresses, okay? So we'll provide more details in this presentation happening today, okay? One thing is, it's not just linear address, the virtual address. We're also extending EPT, extended page table, and then also BTD page tables. Then, in terms of compute, we continue to add more resources to the microarchitectures, right? Number of cores, also new instruction to support high-performance computing or machine learnings. And then one trend happening is basically offload to the accelerators, because to scale more, we need to kind of offload a certain computation to accelerators. Now, that will be helpful not just the performance, sometimes thermal or power, limitation because of the power limitations. And I have some more on FPGA and then SBM. Okay. So in terms of FPGA, we've been working on FPGA actually from Broadwell. And then on the Skylake, we have so-called Xeon plus FPGA. Within a chip, we have a FPGA inside a chip. And then the FPGA is connected both by PCI and then, in this case, UPI. It's interconnect used for example, transporting the data between the processors, right? That's a UPI. And probably I should use this one. Yeah, this one. Yeah, this is the PCI, and then this is the UPI. Okay. And this one is high speed kind of a network, for example, used for the Ethernet, for example. Okay, so you can program FPGA as a advanced switch or kind of a NIC, more smart NIC. Okay, if you use this one. I don't know if you guys know about more, about FPGA, but what we need to do with FPGA is download so-called a bit stream, basically to make new hardware in FPGA, okay? And we've been working on so-called FPGA manager in the Linux kernel, which basically download the bit stream to FPGA, okay? And once the bit stream is downloaded, you're gonna find new hardware, okay? That can be accelerators or Ethernet, whatever, okay? So that's the FPGA works, okay? And we have two connection here, like I said, PCI or the QPI. If we use a PCI, it basically becomes the PCI device, and then today, SRV is available, so we can provide one so-called AFU, accelerated function unit, to VMs, okay? And on Xen, we actually tested HBM assigning FPGA using SRV, and then it worked. So that's the state we have. The other thing is, once we have more accelerators, including a GPU, FPGA, or QAT, quick assist, we really want to make them more efficient, especially in this case, SVM, shared virtual memory. The key here is this, the accelerators basically operate in CPU virtual address space, okay? So this is a new one, and then this is happening. The device used to just look at this level, BTD, but now then they can look at the x86 page tables managed by the operating system. So this is a kind of a new features happening. I expect the transition to this new infrastructure takes some time, but this is gonna happen, okay? And we provide more details again today, okay, here, okay? In terms of HPC, high performance computing, in HPC, actually containers are more popular today, However, some people, even the HPC, they are worried about some security if they use containers, right? So some of them are actually looking at the VM-based, even VM-based containers to have more containment or security, okay? So we actually, I think we presented this last year, Xen Summit, and we continue to work, and then, so today we can run Xeon in VMs, I mean, with the VMX enabled. There we have just one single VM, and the performance will be almost native. It's more than, I think, 95% of native performance we achieved. So, and we have some update on this side. This is an interconnect, right? RDMA. This is a key, the fabric for the connecting the nodes, HPC nodes, okay, to make them scale. And for example, I don't know you guys know, but MPI, right, that message passing interconnect, is a key for HPC cluster to scale. So we actually also tested, in this case, Intel Unipath, basically the fabric technology. Today we can achieve 100 gigabit throughput. Well, good thing is the MPI is you can send the data from application to application directly. So that's, that way you can achieve very high latency and bandwidth. Storage, so we have Intel 3D Crosspoint support, and we've been working on that, but right now I think we targeted at 4.10, but we kind of missed it, so we're looking at 4.10. Okay, security and then protection. So protection keys, I don't know you guys know about. This one is for process to change the permission of a particular range of virtual address space without using TLB shutdown. That way, process like database can change permission about data very quickly. And if, for example, application thinks it doesn't need to modify the data or key structure anymore, then he can quickly set up the right protection to certain data structure. And that'll be there. And then we're working on UMIPs. This is preventing some sensitive instruction in user mode. Okay. That's been done for Xen 4.9, but looks like additional work is required. So we're going to complete in 4.10. Okay. Then SGX, this is a safeguard extension. I'm going to talk about this later today. Okay, more details. And mode-based execution control for EPT. What EPT does is it converts guest physical to machine physical. Now today, without the mode-based execution control, EPT itself doesn't know or doesn't care the mode of the guest, right? Either guest is running in supervisor mode or, like ring 0 or ring 1, or the user mode. So it's kind of agnostic at this point. But with this, now the EPT can check the mode of a guest, what kind of mode the guest is running at, and based on the mode, it can generate, it checks the permission of an EPT and then generate the EPT violation. More coming. That's one thing I really wanted to add to this section. So you can guess that's related to this area. Okay. So anyway, that should coming in a week or something like that. So hopefully you find that will be interesting. Okay. Anyway, I cannot talk about that one at this point. Okay. So other one is then, so once you get large data support and compute and then scalability and then storage, and then you also need to, I think I have a typo here, I'm missing E, but performance monitoring. This is inter-process tracing. We're gonna plan to support in 410, which basically trace that application or the system execution. Okay, basically using CPU, so you can trace that execution about CPU. That's an inter-processor trace. In Broadwell, that's not actually available in BMX, BT in the guest. Now in the Skylake, this the trace PT is available. So that's the reason we're enabling for 10. And then the resource direct technology. We have, again, more details today. And that'll be, for example, L2 level CAT. CAT is, cache allocation technology. Okay. And so that's I think that's overview of what we are doing, and then how we're enabling those features in Xen. Okay. So back to the, I think, original kind of the context. Basically, we are seeing huge data growth, and then we're working on, hardware side to extend to support more data and more compute, storage, network, and then security, and then monitoring. Okay, so those are kind of what we are doing in the hardware, and then also we're enabling those in Xen. And then Xen should continue to be the, the foundation of the cloud and the data center. Okay. With that, I think I would like to take more questions, and I can discuss more. Any questions?
I had one question about the FPGA thing that you shown us. You did that you have done HBM pass-through of the FPGA. Do you mean of the device that was configured? Well, I mean, you flash the FPGA with something and then it becomes a device, I guess, on the PCIe bus, or?
Okay, so I think it's a two-step. First of all, FPGA is a PCIe device itself, okay? So today on this platform, Skylake plus FPGA, FPGA itself is a PCIe device, and you can assign the FPGA as a PCIe device to a guest, okay? Or you can assign FPGA VF, virtual function device, to a VM, okay? That's one step, okay? Once you have access to FPGA, then you download, you need to have a device driver for FPGA, okay? You download the bitstream, okay? Then FPGA become accelerator. Whatever the program you downloaded, basically. Now that accelerator itself may not be, probably it's not the PCI device actually. It's a different device. Sometimes PCI, you could emulate kind of PCI device, but those new devices don't necessarily be a PCI device, okay? So that in the guest, you need to have device drivers for that new device, not the PCI, FPGA, okay? So for example, if your bitstream has, let's say, encryption engine, okay? That's not the PCI device. If that's not the PCI device, then you need to have some driver or library that talks to or manipulate, program the encryption engine. Okay. Does that answer your question?
Yeah, so basically it's, well, you can flash each virtual function with different bit streams.
Right, right.
I think we have time for one more.
Presumably for when you've got a compiled FPGA program and you've uploaded it, presumably even if it doesn't emulate a full PCI device itself, you're still going to have to talk to it through the bar or the I/O bar of the existing device.
Right.
Does that mean that most of the bars will essentially be programmable by the underlying logic? Because if it's not like that, we're going to have a problem passing it through because we won't know what ranges to give to the guest when a new device appears.
Yes. So it's a responsibility of the device driver, and then in virtualization, yeah, we need to actually intercept if to overwrite or emulate the bar address. So that's kind of new thing we need to do that. And that's not, again, if it's not the PCI device, the PCI emulate, it's not, handled by the PCI emulation.
Okay.
So that's a kind of new challenge, yes. And in Linux, we implemented such device as a platform device. So there are some devices that really don't, use PCI, but they have, they use MMIO accessing some bar address. And so again, in Linux, it's a platform. We treat them as a platform device. It's part of a Linux abstraction.
Yeah, I have a question about FPGA. The FPGA you said HBM test with the SROV capability. That means different customers use the same FPGA algorithm, right? It cannot be partitioned and assign different partition to different guests.
Yeah, so we can have a multiple base, FPGA logical FPGA device, and you assign the VF to each VF to each VM.
Yeah, so that means different customers in a server share the same PF. That means they share same algorithm.
No, so you can download the bitstream to each VF.
Oh, you mean that the customer has the right to...
So if the VM or somebody try to download bitstream, that'll be trapped,
Yeah.
and then it goes to the PF. And it's up, PF's responsibility if he can download the bit stream to PF or not.
That means the customer have the right to directly download the bitstream to the.
It's not possible because the VFs don't have that kind of configuration capability. Only available to PF side.
Okay.
Yeah, and the PF can control which bit stream go to which VF.
Yeah. What's the switch time between different?
There's no switch. You don't need to have a switch because it's a separate device.
Oh.
So there are multiple AFU accelerator units inside the FPGA in this case.
Okay, thank you.
Okay?
Okay, I think we're over time, so we better move on.
Okay, thank you.